talking about over here, some of them could be primarily airborne. They spread through inhalation, that is the main carrier of pathogens into the fourth individual. There could also be some pathogens where they may have other routes of transmission through bodily fluids, through contact, but also through inhaled transmission. So this approach can help us understand, even if you are maintaining some kind of social separation from the infected host, but still there could be some chance of getting infected just by breathing in the aerosols. So let's do a quick cartoon of the geometry that we have been seeing for all this week. Now, as you saw yesterday, so basically, as we saw yesterday while running the simulation, even before we run the simulation, when we develop the numerical domain, we need to first know which are the sites of interest along the airway. So let's assume that we stick to the same site of interest as we have been primarily doing over here in this course as an reference, but also I mentioned that, for example, the pox family viruses that we are working on, they actually have their primary initial sites of infection further downwind. But this is just for illustration purposes. Let's assume that we are looking at the position over here. So this is the initial infection prone site for the SARS viruses and also for the respiratory syncytial virus, which is quite common as well. And if you just look up literature on RSV, you'll find a lot of biological data on RSVs. Now, just to make it clear over here, different pathogens could have different trigger sites based on the nature of the cell surface receptors that the pathogen may utilize for cellular entry. And as mechanicians, we won't know what that is. So either you collaborate with the corresponding experts, or you try to understand the literature that is coming out. Okay, so let's assume that in this way, we are tracking particles that are going in. It could also be through the mouth. I have not included that in this cartoon. So let's assume that we are tracking particulates of diameter di micron. So we saw yesterday that we can quite easily figure out what is the deposition efficiency of these particulates at any marked out region along the airway. So let me write this down as comments. So from the numerical simulations, of respiratory inhaled transport, let us assume that the efficiency or the deposition efficiency of the particulates at the trigger site is epsilon I percent. Now, the simulation that you ran yesterday, or we ran yesterday, they were monodispersed simulations, as in, so when we ran the particle tracking exercise for the infection mechanics, we seeded the entire nostril plane with these particulates. We did not impose any kind of size distribution on those particulates. But when we are breathing in, there is a size distribution. When the host is going to expel the ejector, it would have a size distribution. So we need to take care of that as well. So now the airborne dehydrated respiratory ejecta that is expelled by the infected host and now being inhaled by the exposed individual will have a distribution of particulate sizes. Now, you can find this data from the literature, but there is a big caveat over there. So most of the size distribution numbers that you will find, they were collected by putting the test subject in an enclosure. And they tracked the droplets and the aerosols that landed on the walls of that exposure, on that enclosure. So as a result, there is this problem that they are just tracking the sizes that are depositing on the walls. Those droplets could coalesce together to make bigger droplets, and that would contaminate the data on the wall. Relatively, it would be more accurate if you can figure out the size distribution in air, right? As someone is breathing out, what is the size distribution right outside in the air? We can possibly get that with laser diffraction measurements, but it is challenging because the concentration is sparse, so it's not like a nozzle spraying a dense cloud of particulates out into the air. So it is challenging, and I know people are working on this. Also, based on the pathogen concern, so if someone has flu compared to someone with, say, COVID-19, we don't really know if the particulate size distribution is going to be the same for both, right? So this experimental data is getting updated every day. People are working on this. The data that I am using in my work, you will see that I cite papers from 2009, 2010, and I know that some of those measurements are probably not as accurate as I want them to be. So just to know that this is something that could be updated as we move forward in this line of research. Okay, so this distribution, it comes from experimental data. Okay. So this is the first piece of information that we need for our model. Because we ran the simulations as monodispersed, we need to impose the distribution that we will be inhaling in, and that comes from this. The next thing that we need to know is, we know the particulates that are depositing at the infection prone sites, but what is the viral load carried by them? We need to understand what is the concentration of pathogens in those particulates. That again could not be derived by us mechanicians, it has to come from the virology world. So, if Ni number of di micron diameter particulates are inhaled, and coming to the next base, if Vi is the virion concentration. So for this write-up, I'm talking about virus transmission. You can think of other pathogens. You can think of, for example, bacteria as well. The mechanics-based in silico approach that we are propounding here should be valid there too. But let's assume that we are looking at viruses, and if Vi is the virion concentration in unit volume of these particulates. So before I go to the mathematical expression that I'm trying to get at, so this piece of information over here, this comes from experimental mechanics, right? Because they're just tracking the sizes of particulates. But this piece of information should come from virology. And the way they collect this measurement, typically, they would take swabs and take nasal swabs from the infected host, collect that fluid, and try to figure out what is the concentration of the virus in that swab sample. That again could have its errors, as you can probably guess. We are trying to use that data collected in the swab samples and assuming that the concentration in the airborne particulates is same. That's a stretch in some sense. And if you ever get to work in this field, it is important that you highlight that these are the limitations that we probably have to face, and some of these limitations as we move forward with this particular subfield of fluid mechanics integrated with biology, epidemiology, immunology can be improved. So this is going to be an active line of research, hopefully, over the next number of years. So, if Vi is the virion concentration, then the number of virions, again, the in silico method that we have learned could be applied to other airborne pathogens, for example, bacteria that can also spread through inhalation. Then the number of virions reaching the infection prone tissue region carried by these di micron droplets di micron particulates is that number. If I call it, say, NVI, it is equal to the deposition efficiency times the number of such droplets or aerosols getting inhaled, and this Ni is coming from the particulate size distribution, times the volume, so 4 by 3 pi di cube over 8, and volume times the virion concentration in unit volume, which I assumed as Vi, times we have some correction. This correction is coming from the immune responses of the person. So, as I think I did mention that if I am breathing in 400 virions and one of you is breathing in 400 variants, our responses could be different because our innate and adaptive immune responses are different. So there could be a correction factor that we need over here. So I'm calling that eta I. And if the exposure duration over which you are inhaling this particulates is Te, then this is the expression. So NVI is the number of variants that would be landing at the infection prone site based on this platform. So here with this eta I being the cofactor from innate and adaptive immune responses. And as you can probably guess, this eta I can also change for the same individual over time. Because if that person had that infection a certain duration back, based on the virus, maybe days back, weeks back, or months back, there would be some adaptive immune response already inbuilt. And then there is some innate response that is with the person. So at this point, if you look at the works that are getting published, and not too many of us who are active in this kind of nasal modeling, respiratory modeling space are actually doing this kind of modeling. But still, the few papers that are coming out, they typically assume this to be 1. Often assumed as 1 as a conservative estimate. So 1 is the maximum, the peak number, right? Like all the variants are equally potent at starting the infection. But if the person has some kind of immune defense mechanism, then that number can go down 0.8, 0.7. But we are trying to get sort of a safe limit idea derived from this model. So it is okay to place it as 1 for now. But if we get more precise numbers, we can of course correct and possibly report a range of the number of variants that would be depositing at the target site. And later on, I think, or somewhere, I probably have, on my slides that I showed day before yesterday, I have a citation where they actually reported the corresponding numbers, and they thought that it is okay to be assumed as 1 for safe estimates. Te, as I said, is the exposure duration. Now, the exposure duration could be useful in 2 ways. For example, first, if we are trying to figure out how long of an exposure can lead to infection, you can use this approach to figure out the exposure duration that would be the critical exposure duration. Or in other words, if we know that a person has been in contact with an infected host for a certain duration of time, we can figure out the probability that this exposed individual has the risk of getting infected. But more on that will follow on the next calculations. Any questions until now? Okay. So from here we come to the concept of what is called the infectious dose, and I did describe that during the talk. So the infectious dose is the minimum number of variants that can infect an individual, and this is a tricky concept because if you take just one variant and one cell, that one single cell can infect the individual or the cell. So one may argue that the infectious dose is always going to be 1. But because of the immunology, it does not happen that way. So you need to, if you have a particular organism which you are trying to infect a set of cells, you need to provide enough number of virus to make the infection triggered at that cell culture. So it is related to the immunology of the person or the immunology of the cell culture medium as well. What kind of defense mechanism those cells might have to that virus. So people have done a lot of work not us, people from other fields have done a lot of work to figure out the infectious dose of different pathogens. So if it is a known pathogen, we will have the infectious dose number. So if suddenly there is a very bad flu outbreak, we know what is the infectious dose that can lead to infection. So for example, there are different strains of flu virus. For influenza A, I think I mentioned during the talk that it is between 1950 and 3000. So that number of variants can lead to infection. So let's assume that it's a known pathogen, not something like what happened in 2020. We did not have too much information about the SARS-CoV-2 pathogen. But let's assume that it is a known pathogen. There has been enough virological research and we know the infectious dose. If that is the case, so let me write down some comments first. So now comes the important concept of infectious dose, or ID. So ID is the minimum number of variants that can launch infection in an exposed subject. And it is one of the most important virological identity of any pathogen. As examples, as I said, it is between 1950 to 3000 for influenza A, and it is on the order of 100, or more precisely around 300 for SARS-CoV-2. So that is one reason why, if you are trying to approach a new pathogen, it might be helpful to start your work from pathogens for which you know the data, the biological, the virological data. And that's why in our effort to work on monkeypox, we have first started to develop the model for smallpox, because for smallpox, we know the infectious dose, which is between 10 and 100, by the way, for smallpox. We did not know that for SARS-CoV-2 when we started the work. So we had to take another different approach to get to the infectious dose, and I'm going to come to that in a moment. But for now, let's assume that the infectious dose is known. So if ID is known, then from the previous equation, the threshold exposure duration to avoid infection would be ID divided by that NVI that we had derived in the previous step. So epsilon I by 100 times Ni times 4 by 3 pi di cube over 8 times Vi times eta cap psi. Now, we need to be careful here that this equation that we had derived were just for the di micron particulates. We are breathing in particulates of different sizes. So there should be a summation here at this point where we imply that we have covered the range of sizes that we are breathing in, and that's how we do our calculations. We cover the entire range. Now, an interesting thing pops up over here about this virion concentration in the fluid. At this point, we assume that this Vi is constant, but we don't know that for sure because there is also a conjecture in the community that the smaller particulates, uh, the zero point 0.5 micron, the 1 micron ones, they may contain a higher concentration of viruses than the bigger droplets. And that data is still not available. So it depends on how these droplets and aerosols are formed, and some of you guys who are working on droplet research, they might find this interesting because think about a droplet fragmenting, and if there are some contaminants embedded in the droplet, do the contaminants crowd into the smaller subparticulates that are formed? If that is the case, then possibly the submicron particulates would carry, or for that matter, if you compare 2-3 micron particulates versus the 20 micron particulates, they might carry a different concentration of virus. But for now, because we are using the nasal swab samples and they just report this many number of variants per ml of the swab sample, we don't have any way to figure out this difference in the variant concentration. So again, this is an open area of research, so could be constant. So could be dependent on particulate size, and that's why I have it as VIs with the I subscript. But in our model is currently assumed constant. So the pathogen concentration is homogeneous in the respiratory ejecta as assumed as of now. So this is the threshold exposure duration. So once you know for a known virus what is the ID from the simulations, from the fluid mechanics simulations, and then merging that data with the eta response and then the VI from the virology, you can predict at least an ordered estimate of this is the exposure duration. Would it be on the order of minutes or could it be on the order of hours? And that range can vary as much as that. So we would know the threshold exposure duration to figure out if the infect, if the exposed individual who was exposed to a host could get infected or not. And this itself would have relevance for different sectors. So I think I did mention during at the end of the talk that the Federal Aviation Administration, they got in touch with me to get our simulation data. So basically what they were thinking of is on these lines. So think about you flying from here for a 2-hour flight and there is an infected individual somewhere. So in those 2 hours, what is the risk of you getting infected? Versus if you are flying from say Delhi to Chicago, it is a 14-hour flight. And then of course you are going to breathe in more virus. Now, what is that threshold exposure duration when we really need to quarantine the entire, all the passengers from the aircraft? So this can have many practical implications when applied appropriately. So this is for known virus with the ID known. The next obvious case would be if it's a new emerging pathogen. For new emerging pathogens, if ID is not known, but we do know. So for new emerging pathogen, as we saw for COVID-19, or as we see for cases of say monkeypox, there are papers out there where they report the super spreading incidents. So they report certain situations where there was a confirmed host in a set of people, and that led to an infection onset in a lot of other people in that space. So for new emerging pathogens, we need to keep our eyes open for those studies that they report the exposure duration over which infection onset had happened, and we use that time interval for our calculation. So if the idea is not known, but we do know the critical exposure duration for example from super spreader incidents. So, as an example, for COVID-19, the data that I ended up using comes from an incident that happened with a choir singing group. So there were, I think, if I remember the numbers correctly, there were around 52 individuals in that group. One of them was found to have COVID-19, and they were together for 2.5 hours. And in those 2.5 hours, I think 47 or 48 other members of the group got infected. The 2.5 hours is hence confirmed to be the duration over which infection transmission had happened. It can happen over 1.5 hours as well, but we don't know that resolution to the data. But we know that 2.5 hours was enough to transmit the infection. So this is for new emerging pathogens, and this data would be out after a few months of emergence of the pathogen, especially if it is becoming something like a pandemic. And then, if that critical exposure duration is TC, then we can use that estimate to get the infectious dose. So now this would be summation I epsilon I over 100 times small n I times 4 by 3 pi di cube over 8 times vi eta I times Tc. And this can hence generate the first estimate for the infectious dose, which can do wonders if you are dealing with how to curb infection for a new pathogen. And when I first came up with this number for SARS-CoV-2, I got the number to be 330 using that exposure duration. And my paper was on archive by fall of 2020. Eventually, it got published in 2021 after multiple rounds of peer review. But at that point of time, there was no, at least I could not find any biological literature on the infectious dose for SARS-CoV-2. By end of 2021, there were papers coming out on the infectious dose measurement done from the biological and the virological community. And many of them, they started to cite my paper as well, and they came to the decision that it is on the order of hundreds. Based on the study, it could be 300 or 500, but around that number. So that made me really happy that this kind of mechanics guided approach that we are applying with some data coming from, for example, I did use the VI coming from the Munich hospital where they collected swab samples from patients. And then the size distribution came from a 2009 study. So despite these limitations, I could at least predict the correct order for the infectious dose. So this would be useful if we can apply our skills when there is a new emerging pathogen. So let me just write down some last comments. So for more details on mechanics guided in silico approach on airborne respiratory infection transmission. Via inhalation of particulates. You can see this paper that I'm talking about, so 2021 scientific reports. Okay, so, and as I have been trying to point out, there are many gaps as well. I'm not saying that this is end all be all. There are many gaps that we need to address as we move forward with this new subfield that is emerging. Any questions? Okay, so that's all I wanted to cover for the infection mechanics in terms of how we can connect the data that we have derived with the other pieces of information. From here, let's go on to the targeted drug delivery, and I think I could be done within this session. So let's do that. And then the floor is open for Dr. Shamantu to spend the rest of the day. TC. So TC is coming from the super spreader incidence in this case. If the pathogen is emerging, as I am telling that over the first 2-3 months, you will find some papers where they have reported this incidence where one single infected person infected others quite efficiently, and they report that exposure duration. And there were multiple studies with COVID-19. There are multiple studies right now with monkeypox, and you can use those numbers. So this may not be accurate. This may not be accurate. So, for example, from the Kaya group incident that I just told you guys about, they reported 2.5 hours. Do we know what happened at the 1.5 hour mark? That might have been sufficient as well. So this could have errors, but this gives you a safe conservative estimate because it is the TC that was shown to lead to confirmed infection onset in others. But when you don't know enough information about the pathogen, you have to deal with whatever you have to figure something out. It's like walking at the forefront of knowledge at that point. Okay, so the other main translational application that we are part of is on intra-airway, intranasal, intraoral drug delivery. So this is on targeted intra-airway drug delivery. Now let me be clear over here that the previous application, the infection mechanics application, it's an emerging field. There is not much competition in that subfield, and we are one of the very few groups who are active in that space. But targeted drug delivery, respiratory drugs, it's a mature field. There are many groups who are working in this space. Many of them are connected to hospitals. So as young scientists, when you figure out what you want to do, this is an important consideration that sometimes you might have to think about whether the field is new or versus the field is old. If the field is a little old, it's difficult for you guys to get results that would get noticed, for example. Now, when I started in this area, it's almost 10 years back now, so it was still emerging, so that's how I could get in, but it's a mature field. But if you work with a group who are working on targeted drug delivery, that would give you a good training to use your knowledge in other areas. Okay, so on targeted intra-airway drug delivery, so from the simulations, we will know the particulate sizes that show higher efficiency in reaching the target diseased regions. And this is something that we did yesterday. We had that conical injection for the nasal spray, and we could figure out the efficiency of the 10 micron particle to deposit at the target site. We can get that information for size distribution as well using similar approaches. Now, one more thing in terms of my clarification over here. Yes, we can simulate breathing, we can simulate these particulates in the nasal airspace, but there is still this limitation that the data is limited to these particular subjects from whom we collected the CT scans. So there is always this question how uh, extendable these findings are for a new person. So let's assume that I know what are the good particulate sizes for my area, but what about your area? They could be different, right? And when this field started, the main goal was to do personalized healthcare, to reach personalized healthcare for nasal drugs, and that is still something that we have not managed to achieve because each area could be different. So it is always interesting to think about what are the generic trends of particular transport in the nasal space, and that's why I'm moving gradually to some parametric analytical modeling as well because that space is new. Folks who are doing this kind of research, they're using CFD, they're working with the doctors, but they are not doing the more generalized analytical modeling, and that could be something that might be useful. Okay, so once we know the efficiency, the information can help us design better drug delivery products, formulations, and protocols. By products, I mean we can, and in this case, even if you are not thinking about an academic career, that has a big relevance with industry. And that's why we work with a number of pharmaceutical companies. So if you ever get to work in that space, uh, even if you don't have new ideas to work on, but still these skills are very useful in the industry, in the drug delivery industry. And that field is becoming bigger in India as well. It is still a new field, so that's good. And we work with around 4 or 5 companies who want to get our knowledge in improving their products. Now, in terms of improving their products, what I mean is you did the simulation yesterday, right? So in terms of the product features, what were there? There was the cone angle. You can change the cone angle. There was the exit speed of the particles, which we assumed as 10. That could be tuned as well based on the delivery device. We placed the spray a certain depth inside the airspace, right? So think about a new kind of spray device. For example, the one that we used, we were thinking about the spray nozzle like this, right? And we were trying to make sure that the axis hits the target site. Now, I'm working with a company, they're based in Florida. They are trying to develop a slightly new design for this. So they have an adapter which bends like this over here. So the mechanism is, they have already patented the mechanism, and then as you pump the fluid, it goes in like this. So this angle could be tuned based on the person. So the doctor can look. Someone asked me like, how would we replicate this spray axis direction in a real subject. So the doctor takes this device and looks at the anatomy and then fixes this particular angle for the person. And then once that person goes back home, they can just keep on using with that particular angle. So in terms of the product development, there is a lot of work that can be done. And with this kind of pathogens, the respiratory diseases are actually increasing as we face other challenges to our society. So this is a very growing field. And we recently got another grant where, because it's a growing field, the US government is also putting in more resources in the industry sector as well. So this is for the product. Now, in terms of the formulation, what did we use? We used the density. We used the particulate size distribution. Those could be tuned as well by changing the formulation type. What we did not use in our simulation was viscosity. We did not really care about the viscosity of the material. But if you think about the particulates that are landing in the outer parts of the nose and then moving downstream with the mucus, that viscosity could be relevant. How the droplet interacts with the mucus. The surface tension could be relevant. How the droplet spreads out on the mucus. And that would give the initial coverage region, and then that would move with as we move the mucociliary stream further downwind, it will move. So those features, the density, the viscosity, the surface tension, the particulate sizes are all properties of the formulation, and those could be tuned as well. Finally, the protocols. The protocols, there is relatively fewer things that we can do. So the one work that I showed was compared to the current use spray duration. If you just change the angle, you get a better drug delivery even with the existing products. But the protocols, if the companies decide to embed that into their device design, again can lead to new kinds of products. And this is just for the nasal airspace. You can think about the oral drug delivery as well, and the same parameters hold true over there. Okay, so the information can help us design better drug delivery products, formulations, and protocols. And this is to develop something new, right? In terms of new kind of device, new formulation, new protocols, but just using the approach that we have established in this class, you can help out the companies to predict their spray performance. And that's what we are doing as well with some of these industry partners. They want to know how efficient their products are in reaching the target infection sites. So we can also use the computational data to assess the efficiency of existing drug products using their product parameters. And that includes what is the height of this nozzle? What are the particular sizes in that existing formulation? What is the viscosity, density, cone angle? We can just get those information from the company, and then we can give them, this is how efficient your product is to treat this particular pathogen versus the other pathogen. The target site is being different. And this is not intellectually that exciting for us, but still that helps to pay some of my graduate students this kind of work. Okay, so now in terms of the calculation, when we are actually trying to understand the efficiency of an actual spray product, we need to also think about how much volume of the formulation would be pumped in one single pump, because that determines how many particulates of each size are there, right? So if V is and that volume is called the dosage volume. So if V is the dosage volume of a particular spray in one shot, and NTI, I'm using the subscript T here to differentiate from what we did in the previous slide, previous page. So this is for targeted drug delivery, so hence the T, NTI particulates of size TI micron deposit at the target site. So in that case, the targeted drug delivery efficiency is the volume that is deposited thanks to the particulates that did end up at the target site. So I'm going to cover the entire range of particulate sizes. So summation 4 by 3 pi Ti cube over 8 times Nti, and yeah, so this NTI is the number of particulates that are depositing, so the efficiency is not there. The NTI is being fed directly from the CFD. This divided by the V times 100. So this NTI is based on the CFD predicted efficiency, where NTI is the epsilon I over 100 times NP. And we saw this epsilon I derived from the 10 micron yesterday in our work. And this NP is the number of particulates of that size present in one single dosage volume. And that comes from experimental data again. So NP is the number of particulates of that size in one dosage volume. And hence this is related to the product's particulate size distribution. Now the main thing, one of the main things that these companies are working on is to achieve finer particulates, because eventually they want to send the drugs into the lungs, because that's where things get tricky in terms of fatality of the disease. And we know from our analytical computational studies that we have done this week that to reach the lungs, the particulates need to be very small, right? Unfortunately, in the current products, the median sizes are around 30 to 40 microns. They are not very efficient at reaching the lungs. To reach the lungs efficiently, you need to be consistently within the sub 5 micron range. At worst, sub 10 micron. And even sub 10 micron is a challenge. So that's what many of these companies are working on, and we do have some partnerships on that as well. So making the particulate size distribution move towards the smaller end of the spectrum. Okay. Now, just as a quick note on how they measure this size distribution, if the spray nozzle is like this, they're emitting the particulates. They pass a laser sheet at a certain distance away from the nozzle exit. So let's call it the laser plane, and then they get the laser diffraction measurements. Which, along with the size distribution that is passing through that virtual plane, We also give the speeds of the particulates as well. So if you move the pen closer to the nozzle exit, you will get the exit speed. We use 10 meters per second yesterday. If you go back and look at the papers that we typically cite in our studies, the range could be anywhere between 3 and 19.2 meters per second to be exact. We take just the sort of like the middle number there as 10 meters per second. Okay, so for more details on this approach, you can look at the studies that we have been publishing. But in terms of the papers that I had added to the cloud folder, read the Basu et al. 2020, and this was also published on Scientific Reports. This first paper has a very nice experimental validation, as in uh, validating this is always a challenge, right? We cannot get this data in a real subject. So what we do is get the 3D print. But even after getting the 3D print, how do we track where the particulates are landing? So in that study, we collaborated with an experimental group. They did what is called the gamma scintigraphy imaging. So gamma scintigraphy imaging can image the radioactive signals, and that would be very precise. And we are using that technique. That technique was developed from the physics community, but now we are applying that technique in this biomedical research by putting by taking the nasal spray solution and then adding some radioactive marker to the solution. So the radioactive element that we used was technetium. So we added some technetium into the solution. Then we spread it while passing air through a pressure pump through the 3D print. And once those solutions have deposited, then they use the gamma camera to image the radioactive signals. And they're very precise. So each of those particulates, they were emitting the signals, and then we compare the signals coming from different parts of the airway compared to what we get in terms of the delivery projection from the CFD. And that matched up. And that was this study. Now, part of that work came from UNC. After that, the more recent work that we have published was this one. So this is by my grad student Akash. So this was published in Frontiers in Drug Delivery. Now for this one, we did not have access to as sophisticated of an experimental measurement technique. So we just looked at the penetration of liquid volumes through the 3D print. The more interesting thing on this paper was changing the how for existing products, if we just change the direction of the spray, how things change. And we saw that that changes the targeted drug delivery by over 100-fold sometimes. And it always improves the drug delivery irrespective of the individual anatomy of the person. Now, based on the anatomy, that improvement could be 300 folds, that improvement could be 50 folds. But on an average, the improvement was around 100 folds. And I showed that data in my talk as well. So let's end it over here. I do want to discuss some or basically brainstorm some open questions that we can think of as a community moving ahead. But we can keep that towards the end.
The last session.
Yeah. It would probably take like 15 minutes at most.
Okay, so maybe like the next session I can just wrap up that derivation.
Yeah.
And then after that, we did read like
Yeah.
maybe the like the last half an hour of the videos you can again like
Yeah.
just summarize the whole course.
Okay.
Open
Okay. Okay. Is it stopped?
minus rho u dash w dash mu. And then we said that this the tau capital Xx involves the velocity gradients or the mean velocity gradients rather, and these are the terms which are arising because of the momentum flux due to the fluctuating components. These are actually not stresses. However, when results need the decomposition and like rearrange this, just to honor his name, these components are the Reynolds stress, and we also yesterday wrote the matrix form minus rho u square u dash v dash u dash w dash. Similarly, this one, the diagonal components v dash square and w dash square is just like this. In v dash w dash here and v dash u dash here, then w dash u dash and w dash v dash here. So these are the components of the Reynolds stress. And then we said that like these components are equal to each other. So W dash U dash these are. So there are 6 unique components, and we said that like due to the evaluation procedure, there are these six new components. We have no way to know their like quantities, how to estimate them. And we said that if you want to get another governing equation regarding these quantities, you will generate some quantities involving again like this rho ui ug uk. So you can see the problem is never solved, and like the number of governing equations are always less than the number of unknowns. So then we said that it is a turbulence closure problem. So after that, like that was the last yesterday's discussion, and then like today we will like show here these quantities are anyway we know that u dash square, v dash square, w dash square, those will be the negative terms. But in general, what about minus rho u dash v dash? So a very simplistic model of let's say a flow over a wall where the u direction velocity is like a function of y. So let's say at a given height y1, this is uy1, a little higher height uy1 plus l, and a little lower height uy1 minus a. So now let's imagine there's a fluid element here in the intermediate flow, and the fluid element, what is like there is a positive fluctuation of the velocity which just वही करते हैं. So here the fluid element, let's say there is a positive element goes in the upper portion. Essentially this fluid element with its lower u velocity mixes here, right? And then since this is lower velocity, the overall velocity like the u component that will decrease due to the mixing of this region. So here u will decrease because these components have a lower u velocity. So then like you can say u dash is negative and this one is positive. So u dash v dash. So then since u will increase here, this u dash fluctuation will be positive. So overall again v dash u dash is negative. So in general u dash v dash is negative, and then minus rho u dash v dash when you do the evaluation procedure turns out to be positive due to the negative sign here. So this is a very simplistic picture of showing Obviously, it's not that rigorous. You can always argue that only it is like in the without any wall how you prove, but this is just a simplistic picture to show that in general the uterus fetus will be product will be always negative. Okay. So then now earlier, like if you remember, we said that like the del del x tau xx plus del del y tau yx plus del del z tau zx. If we individually write, we can, let's say we take the t component here plus this will be 2 mu del u del x plus del del y mu into del u del y plus del b del x. Similarly, this one del del z will be del u del z plus del w del x. So the pressure component is as it is minus del p del x plus we can rearrange one like we take the mu outside assuming that it is constant throughout the fluid. So del u del x we just write down to del u del yeah, each other and we are writing around 5. So people will do the simulations or experiments like this A like 0.35 to 0.45 and this one is like not exactly 5, it's like 5 plus minus 0.5. So these are the like when someone tries to simulate the flow near the pipe, these are the guidelines based on which you can carry out the calculation. That let's say like near to the wall we are know the formula u plus u y plus out. So this region it has some sort of scaling relationship. You can find out like if you like do the literature survey of flow in like one bounded domains, you can find out the scaling relationship. Some people have tried to given a formula. In this log region, this is the governing formula. So in this way, like there are three regions. One is the viscous sublayer, one is the buffer region. The buffer region is basically the region where both the stress components are like equivalent with each other. In the log law region again, the mean velocity gradient is much less dominant compared to the Reynolds strength, and in this way there are these three layers very near to the wall. Okay, so this is again this derivation is just done assuming that the wall is very smooth. Sometimes there can be flow over very rough walls. So in that case, like let's say if the roughness can be quantified some mean quantity, like let's say in this case, like some sort of undulating surface, if the mean height is s for a flow over a rough surface, and s is the mean roughness height, then in the log law region you can write 1 by k ln y by s plus b. Again, you can see instead of y plus, it is normalized with this mean roughness height. B is again a constant. B I don't remember. Obviously, this B will again change from scenario to scenario depending upon the mean roughness height. So, just another quantity I wanted to just discuss, just like the turbulence, there is also the intensity or degree of turbulence. Let's just write that. So, I equal to 1/3 of u dash square plus v dash square plus w dash square by some sort of characteristic velocity or free velocity, center line velocity, whichever is the like for flow over a wall, this u infinity represents a free velocity. For pi, some sort of mean velocity. This is the like it will divided by u infinity. In case of isotropic, by definition, these three quantities will add up and they are equal to each other. So isotropic, again I am reciting the definition. So this quantity becomes 1 by 3 into 3 u dash square by u infinity. So eventually it becomes like u dash square. So these three gets cancelled out by u infinity. Okay. And you remember the kinetic energy is 3 by 2 u dash square. So u dash square for the isotropic turbulence, you can write like this 2 by 3 kinetic energy. Okay. So the intensity is again like if we have information about the kinetic energy, we can write this I as 2 by 3 kinetic energy by u infinity. This is the intensity of the turbulence. Okay, so anyway, there is maybe I can spare just well, spare me one or two. So just writing down the 2D flow over a flat wall. So 2D flat plate bounded layer flow. If you recall that the basic equation is rho into del V plus, we are dropping out the steady state term. You can write u del u del x plus v du del y equal to minus 1 by rho dp dx. So if you recall, into the flat plate boundary layer, it was shown by order of magnitude analysis that del p del y is 0. So therefore, you start with the assumption that p is a function of x and y. Then, since you are showing that p is not a function of y, you are converting the partial derivative term into ODE term. So you are writing like this dp dx plus, again, if you recall, we are only writing del to u del y square. The basic. Oh, sorry. Yeah. So here, like if you recall again, by using order of magnitude analysis, we start with the viscous terms del to u del x square plus del to u del y square, and then we show that the second order derivative with respect to y is much higher than this term. We drop out this term, we keep only this term. Then if we carry out the Reynolds evaluation procedure here, so we turn up It will be like this: u bar, then u bar del x plus v bar, then u bar del y equal to minus y by rho dt bar dx plus again here let's write like this. No, del y mu plus mu t del u bar del y. So these guys I wanted to like just writing because I just thought last week only the 2D factor in the convective transfer course. The turbulence, the counterpart for the turbulent flows over same set of geometry will be like this. So that's a brief discussion of like how we like tackle the some sort of approximate expressions for the flows over the walls, and we'll meet at depending upon the lunch. If it gets over by 1:30, we can meet at 2. If it gets little delayed, we can start at 2:30 maybe, so that I can just give the that presentation from 2:30 to 3:30 at max. You just wrap it up with the like the things which you can do in future for maybe 20 minutes around. We will discuss like the role of fluid dynamics in disease transmission, tuberculosis, all these are airborne diseases. Then, like you all said, like we all ever knew, like how 6 feet or 2 meter, like the physical distance maintenance on what is the basis, and then our mass sufficient for protection. Maybe schematic of the 4 stages of any disease transmission. So the first part is more like some biological terms. The first one is like extraction and encapsulation. We did not bother about that, but you can see here the instability is there. Again, for disease detection, we need some sort of laboratory kind of diagnostic tools, which involves our knowledge of microfluidics, surface fluid pathogen interface, how the fluid like contaminates the surface, that can depend on the mobility of the surface, whether it's hydrophilic or super hydrophobic. And then like the pathogen fluid interactions, that can also maybe like sometimes either the droplets become into smaller droplets or the bubbles, they can burst and they can spread the pathogens. Similarly, although we don't know anything about symptomatology, you can see so many like hydrogen phenomena is written there. Just like that, pathogen physiology here also phase change, interfacial flows, adhesion, absorption, the fluid film droplet, these sort of microphysics is involved here. Here also, like pathogen penetration aerodynamics is the last stage when the exposure and infection is taking place. So as you can see, the first part is really done by the doctors and the biologists. In the second box, here we have some expertise. Then most of us are either mechanical or chemical engineers. That could have been applied 100% also, like Manoj sir and his students. So everyone can chip in the second one. So these are the different stages in each different physiological stage. All the aspects of fluid dynamics is tabulated here. Some day-to-day events, like one of the like this is a kind of particle tracking of the curve staging. You can see comparison of the tracks detected from high-speed trains using the particle tracking velocity method. So basically, we will track the of the droplets and the speed and how much it gets like spread out. So here coughs or sneezes, spread of droplets from bursting bubbles, splashes from wet contaminated surfaces. In the next figure, you can see here. So this is like a image of a person. You can see this is the mouth through which like someone is coughing or sneezing. That figure. Here, the figure B, like as I was saying, like let's say some leaf is there, some infected kind of virus which can like affect a plant. Let's say some droplet is like falling here, then this is a again a flexible surface. It like kind of bounces it back, it spreads to another plant, and in that way, plant can also spread some like virus affected or pathogen affected droplets here. This is like one of the high speed jets when one passes the toilet, someone has taken photo, and so this comes basically in the form of jets, and also it breaks in the form of like smaller droplets and can stay airborne. This is like let's say a bubble which is eventually bursting up and releasing. You can see many small droplets here. So these are the instances which you can readily relate. So, in context of like when we cough or sneeze, there are some observations like isolated drop or like a collection of drop. So here, the respiratory drops are like basically the drops which we release in the form of coughs. They are in the range of 1 micron to 1000 micron. 1 milliliter is equal to 1000 micron. Then it can happen that it drops on the floor and it eventually evaporates. That solid residue itself can be like responsible for the like the disease transmission. And this solid residue after the evaporation, this is called droplet nuclei. This is just a, like a jargon, and these are in the order of 10 micron. And these first sort of how these sort of droplets evaporate and how much they stay airborne, this was first studied by this scientist called Wells longer in the first half of the 20th century when he was studying the how the TB it transmits. So he measured the evaporation time as well as the settling time, but he observed that when the droplets are bigger than 100 micron, you can see that it basically within 1 second from the moment we release, it settles down. So these the setting it can be when it evaporizes, you can see then only the solid residues goes up the droplet nuclei. But
What do you think? So,
so you can sit in the past because I have a lot of knowledge here. He can like readily compliment. Like that.
what do you think? So, in our
Within 1 second, he basically calculated what is the distance along which the larger droplets settle down. So that is 1 to 2 meter. And then the smaller droplets, it stays airborne. Just in case many times it has been. So based on that, it's like 1 to 2 meter. Like 1 meter is roughly 3 feet. So the 2 meter or 6 feet, we like go or some whatever some Hindi slogan was introduced during COVID. That was like it was based on this slogan. Like, so it was long back. It was like already observed. So that kind of empirical safe distance is given here. And so one thing it was written that like the impact whether the large droplets are mainly responsible or whether the smaller, more long time airborne smaller droplets are responsible, that is individually like whose contribution is more important, that is kind of difficult. So the WHO or the regulatory body they didn't say anything particular that which droplets are more responsible. But as you can see in the mask design, like first we used to wear the normal the dispensary mask. Then later we were told to like wear the N95 mask. So basically the N95 mask, I guess they can screen the more smaller droplets. I guess that is the reason. Okay. So then like here is the curved droplet, and when someone tries to model it, these are the initial parameters: volume, density, and the buoyancy. The ambient density is rho a, that is the air, gravity, and the momentum. So one tried to model, it has been observed that it is like a kind of jet or thermal plume, and it is expanding like in a particular form. We'll come to that. So you can see here that it is still. So yeah, somehow this was some. So this is called jet interface. You can see basically we release some sort of fluid, it gradually entraps the surrounding air. So there is, you can see laterally this entrapping some air, the fluid momentum basically it becomes much more wider. So that has been only like just schematically described here. And here you can see the Wt is basically this W, the lateral velocity, is described as alpha of ut. If ut is the axial velocity, alpha is the entrainment coefficient. Again, here you can see that when one started the droplet, the dynamics of the transmission of these curved droplets, it can be seen that the larger droplets they quickly fall down, and based on the distance till which the larger particles are airborne, you can see from her mouth to the this you can see this is falling along the trajectory, and this extent is called the range of contamination. The range of contamination basically that kind of determines the safe distance from which one person and another person should talk or whatever like any sort of interaction should be maintained keeping this physical distance. Now, this sort of jet, as I said, this entrapment, like if you look, it's basically from the Stephen Pope's chapter 5, it's about the free shear layers, like it's mostly about the turbulent jets. So you can see here, this is a velocity profile, which is like very near to the mouth, or in context of biological systems, you can say a point of acceleration. So this is x by t 30, this is x by t 60, which means it has progressed further. So the maximum velocity has reduced. It has, like you can see, the width has increased. As it has crossed x by t to 100, the maximum axial velocity has decreased, but the width has been like increased accordingly. And then the shape we have called like the jet entrapment, it's a self-similar behavior because just like when you have studied the 2D flat plate boundary layer, we have studied the glacier similarity solution, right? So in the glacier similarity solution, what we do the like u by u infinity and plot y by u, and then we say that at all locations, if we non-dimensionalize, the velocity profiles will match. Likewise, here also, if we like do the u by u0 is probably the initial maximum velocity by the distance, the central, this one, like the axial distance by the initial, the r half, that is the one half of the central jet initially, then it looks like this. So it essentially overlaps on one another. That's why it is called self similarity. So this turbulent gas cloud which we are saying like the coughing or sneezing, in general, if we don't like keep in mind like the biological aspects, these are known as turbulent puffs or jets. In context of geophysical flows, let's say some sort of volcanic eruption is happening, so that those are called turbulent fumes, or these like let's say in the seabed, whatever sometimes the geothermal vents like some sort of like holes are there in the seabed through which the hot gases are emerging out. Those are called thermals and plumes. And here you can see the thermals and plumes are buoyancy driven, while puffs and jets are momentum driven. So let's say like if we study like whatever is the dynamics of the like the turbulent like nozzle after the combustion. So you will know like going after the combustion through a nozzle, whatever is the exhaust, it releases in the form of jet. So those features, if we study those features, the observation of self-similarity and the entrainment hypothesis observed there can be applied while modeling the curved jet also. Yeah, so then we said here the trajectory of the axial droplets have analogy with geophysical flows with river in outflows. So let's say some sort of like river in outflows is basically like let's say a river in the delta region is entering in the ocean. The way it like initially enters like with a large velocity, but eventually it kind of diffuses out. Or the industrial waste, like from industry, let's say any oil refinery, and when it dumps in the river, such sort of large volume initially comes in the form of jet, and eventually it kind of disperses out. So those features will be like these biological flows. So these long sentences you did not bother, like there's some quantities like the air volume emitted, you can see 500 ml for regular accelerations, but when we like impart momentum while curves or squeezes, it changes to, it has increased to 1 to 4 liter. Likewise, I don't know what is tidal breathing, you know?
tidal breathing, yeah. So tidal breathing is basically a measure of the inhalation rate. And how it is measured, if I remember correctly, it is probably, yeah, let's not say something which is inaccurate on video, but yeah, it is a form of measuring the inhaled air flux.
Okay.
So basically it should be the inhalation rate that we have been using multiplied by some factor.
Okay, so you can see for a tidal breathing, and then when we compare the curve and the sneeze, the duration of the emission has changed. Likewise,
one quick thing, that point where we introduced the formulations for the breathing rate, remember for the adults and for adults and females. So that paper that I cited over there, if you are interested, you can go into that paper. There you go through all these definitions for exactly.
yeah, so you can see here the Reynolds number for normal breathing is 10 to the power 3, but since we are importing much higher speed during coughs or sneezes, you can see the Reynolds number has increased by 1 order magnitude, that is in the order of 20.
So the last sentence you see normal bracket tidal breathing. So
okay, so it's maybe like the relaxed breathing. Okay, yeah. So you can see here that all the parameters compared to the normal and the whenever the high momentum is involved, those are quite different from each other. So these sort of physical quantities one have to remember while modeling the like when you are applying simulation features. So now, like, what is the fragmentation of mucous salivary fluid? So sometimes, like, we know that our cough contains mucus. Once it releases from our mouth, how does it break down? So you can see occasionally the mucus contains like mucin, some sort of biopolymers, protein salts, and moreover, due to the presence of these biopolymers, it is viscoelastic in nature. So the fragmentation is also important. So these are the side views and the top views. The cup being released from the mouth. Some high-speed imaging has taken place, so you can see occasional long filaments, was or beads on the string. Occasionally it will be like these, like long filaments in between some sort of bead structure. So it's as if like the beads are interspersed between the thin filaments of liquids, that's why it's called beads on the string structure. And we also know that compared to water, whenever there is polymer, due to the fluid elasticity increase, the beads, these BOS structures will appear, and these ligaments will take much longer time compared to the water filaments. So here, obviously, the breakage of these liquid filaments, these are governed by the interfacing mechanics, and many of us know the when we involve surface tension, there is Weber number which is rho b square by b square a by sigma, that kind of takes care of the competition between inertial force by the interfacial force. Similarly, like in any interfacial force, instead of Reynolds number, we take into account the Weber number to take into account the competition between inertial and the interfacial force. But let's say we also want to change the different kind of like fluids with varying viscosity. So then, one is on the number, you can see it is the ratio of viscous force by inertial force into interfacial force. So the formula is this, but you can see it can be also expressed as square root of Weber number by the Reynolds number. Bond rate, obviously, the gravitational effect will be stronger. So here, the bond number basically it tackles the ratio of gravitational force by interfacial force. So when bond number is much greater than 1, you can see that larger the diameter of the drop, the d square term becomes dominant, and then the effect of gravitation is naturally higher compared to the interfacial force. So, and these can be also like expressed as two length scales. So here this is d square. We take down sigma by rho g. The square root of sigma by rho g is the capillary length scale. So capillary length scale, and for water and temperature around 20 or 30 degrees Celsius, for like mostly we find that it is around 2.5 mm is the capillary length scale. So these bond numbers are also important while we take into account the path dynamics or the fragmentation of these sheet dynamics here. Yeah, so again, just like the capillary length scale, capillary time scale is defined as the square root of rho d cube by sigma. So basically, like let's say if we release a free droplet, the oscillation, like we can see that the droplets kind of change its shape while it falls down. The time scale of the change is governed by the surface tension as well as obviously the diameter of the droplet is there. So this is a combination. You can find out like by calculating putting the dimensions of this point, it will eventually find the unit is in time like of second. Okay, so here you can see lowering the surface tension will enhance fragmentation into more or smaller droplets. So here this is a fact, like if we if add surfactant to the base water, it will be easier to form smaller droplets. So basically like in order to fragment, what does it mean? Like it essentially enhances the area, then it breaks up. So that requires some energy, right? If you want to expand the interfacial area, it requires like interfacial area into A, sigma into dA. So what to be done is sigma dA. So the point is that if we reduce the sigma, the work requires less. So that's why it is written that for easier fragmentation, if we add surfactants, it will be more easily breaking up and releasing smaller droplets. Likewise, another feature, like just a little bit of trivia about the viewer structures, you can see. So these are some figures from the Gareth McNeil's group, published in Nature Physics 2010. You can see it later. So these, like let's say, the saliva in our mouth, someone has tried to do some sort of like stretching between his hands, and you can see that it has formed some sort of filaments here. Likewise, some water soluble polymer, it can be elongated. So these sort of like if you try to do it with water, this sort of like long lasting filaments will never appear. Again, here you can see the satellite beads are appearing. Even further, it is termed as sub-satellite beads. So these are the features of beads on a string of thing. In our group also, we can, like we have seen, like when we have dropped this 1500 polymer concentration on a superheteroid surface, not exactly beads on a string structure, but some sort of liquid filaments are appearing here. So you can see during the retraction process, thin filaments are being formed, and these are like long lasting enough to cool down the bigger part of the droplet. In case of water, during the retraction process, first of all, these filaments, even if it forms, it will last very few seconds and it will break down. The water will like just get rebounded. On the other hand, with same set of polymer concentration, you can see in the inclined plane that let's say a droplet is falling down of same polymer concentration, you can see how much it gets stretched. Okay, so this is 60-degree, but you can see the stretch like with a much powerful lens. You could have seen a like a actual black line here due to the lighting and due to the like lack of magnification. You can't see the proper like thin ligament being formed. These filaments are essentially features of any non-Newtonian drop impact dynamics. So these are observed by Shomo, who has passed, and Khusro also has seen such kind of things. So here is again just Khusro's recent paper. He has shown that you can see that this is like the effect of Weber number on the retraction dynamics of 2000 ppm drop on the NCZ surface. NCZ is a different kind of superhydraulic surface. You can see here that at the lowest Weber number, it just drops here. This is the top view of the dynamic. So as we increase the droplet, this is the ring, and from the ring, what happens in case of water? It basically, due to the rim instability, the rims get basically some sort of finger-like structure happens, and in case of polymers, some sort of small bead-like structures appear here. But non-Newtonian fluids have sufficient elasticity. In case of water, these sort of thin filaments they fragment, and then you can see secondary droplets are breaking away from the main droplet. Here, what is happening that due to the fluid elasticity, these thin filaments are always intact throughout the reflection process. This never breaks, and eventually it again comes back. And this is a paper by Senior Somo. So what he has done is simply like allow the non-Newtonian drop to fall on the cylindrical surface. For a cylindrical surface, since the observation time is much longer, you can see the what happens in case of water. Like let's say this is cylinder, the droplet when it falls down like this, it stretches, but due to we know the capillary breakup is governed by Rayleigh-Plateau instability. So the Rayleigh-Plateau instability, like within 4 to 5 milliseconds, these long filaments will break up. But in case of polymer, it gets stretched and stretched. We know that in the non-Newtonian fluids, the extensile viscosity is much higher compared to the shear viscosity. That keeps these long stretched filaments sufficiently long lasting, and you can see the emergence of small waves. So, although like in a different context you study the drop dynamics, what I am saying, the ligaments which are appearing in the cup can be also observed in this kind of droplet dynamics here in case of the non-Newtonian flows. So now when we discuss the non-Newtonian flows, there are two relevant non-dimensional number. One is the Weisenberg number. Weisenberg number is the ratio of the polymer relaxation time. By polymer relaxation time, we mean that the polymer, if we can imagine some sort of spring-like structure initially they are coiled under high shear, they stretch. So the time scale over which the stretching takes place and again it gets back to its coil or the equilibrium state, that statistically average time is called the relaxation time. By the flow time scale, this should be lambda gamma dot. So it is basically Weisenberg number equal to lambda 1 over gamma dot. So this becomes lambda gamma dot. So that is a wrongly typed. So this is important, this number. Whenever the Weisenberg number becomes greater than 1, this means that the non-Newtonian features will become sufficiently strong, like whatever let's say we are saying elastic fluid. At when the fluid is like moving at a very low velocity, the polymers are not stretched enough. The fluid is not able to exhibit its elastic property. So then, Weisenberg number greater than 1, it implies onset of elastic instability. In case of pipe flows, unless we exceed the Weisenberg number greater than 1, we can't see the drag reduction. By drag reduction, again, this is slight digression from the disease transmission, but since we are discussing anyway, so earlier we said that this is the laminar flow, this is the laminar flow 64 by Re, and this is the 0.3164 Re to the power minus 1/4, scaling this for turbulent. If we use polymers in the turbulent state, in presence of polymers, the friction factor may be somewhat lying in the intermediate zone. So let's say at a Reynolds number 10 to the power 4, 10,000, the normal Reynolds number friction factor is here. If we mix some sort of polyethylene oxide or TAN, this friction factor will be lying in between. So that is what happens if the Weisenberg number exceeds 1. Now, just like the Weisenberg number, many people prefer the elasticity number. Elasticity number is the ratio of Weisenberg number by Reynolds number, and by these two ratios, numerator is dependent viscosity. So let's say the viscosity of two fluids is same. If we increase the lambda, that will increase the elastic number. So higher the elastic number, higher is the elasticity property of that. The water mixture is obviously much higher compared to the water. So in that case, the elasticity number will be obviously higher compared to the water plus GIAN solution. Okay, so we are discussing the fragmentation. Regarding the fragmentation part, there are many sort of hydrodynamic instability also involved. Hydrodynamic instability itself is like a one semester or two semester course involving long equations. But here, just to cover the responsible hydrodynamic instabilities in the fragmentation process, is like the first one is Kelvin-Helmholtz instability. So basically, this happens when there is a difference between two fluid interfaces. So here, let's say initially there is some white cloud, and this is moving at some distance. The wind over it is moving at another distance. Due to the interfacial velocity difference, there will be Kelvin-Helmholtz instability appearing in the flow. Likewise, as I said just few minutes back, that the BOS structures can like withstand the onslaught of the electrical instability, but this is this is the review paper. But if you just want to get a basic idea about what is happening in instability, you can read this book by either Resin, Resin, or Resin and Similarly, like the Rayleigh instability, there is another sort of instability, the Rayleigh-Taylor instability, when, like you can see, when the lighter fluid is pushing the heavier fluid. So let's say initially, like the water is heavier than oil, so essentially, since it is an unstable system, the water will tend to push through the oil, right? So that creates this sort of instability. So what the this review paper, Eggers and Villermo, they like kind of suggested that the fragmentation process is obviously a complicated process, and this is a combination of all these three hydrodynamic instability processes. Yeah. So this is a new term. It's not a full screen. So this term, yeah. So this nosocomial pathogen transmission, by definition, it means that the pathogens which are transmitted by the respiratory route, sorry, means other than any respiratory route, like if there is like let's say other than like air transmission direct, if these kind of things happen, then let's say drop some sort of like a long jet or the splashes from surfaces of the toilet flushes, basically the water impacts the surface, then it releases the smaller droplets in the air. Here the relevant Weber number is 10 to the power 3 to 10 to the power 4. So this figure you showed like we showed earlier, this high speed imaging of droplet trajectories emitted from a high pressure flush of a typical hospital toilet. So essentially someone actually like made the hypothesis. I think the writer herself and the student like obviously not went to the bathroom, made some sort of setup and then did the flush, and then they studied like if we release some sort of high speed water in the toilet flush like setup, how will the reflected droplet trajectories look like? And they said that from the droplet trajectories, this can rise quite high, and this sort of liquid jets has a high tendency to break up into much micro level smaller droplets.
So one thing over here, so the word nosocomial does not come from nasal. It is related to anything that is happening in a hospital setting. So because there, whoever, if you have patients there already for injuries that might be already transmitted in nature, so nosocomial transmission is pretty common, and there is a good body of literature on that as well.
So this is like seeing the droplet trajectories and the subsequent release of the smaller droplets. they have studied how far these, you can see these dotted lines are basically the jets jetting out from the flask. You can see the relative fluid volume fraction. So they have kind of some sort of made some contour map of the fluid released.
That's why my wife asked me to close the lid all the time.
Okay. Yeah. So like when this paper came, then like people actually made this sort of conscious decision. Like because it was COVID times, everyone was in the like unless we have light setting, we don't follow the good practices. That is sad but true. So, like you can see that this has to like be like leading with the splashing dynamic. Here, like I will show some case like one of your group mates, Manglis, has studied like how the splashing dynamics is affected by the presence of polymer droplets. So here you can see that let's say what he did, like made a simple water film and then like he made some different kind of solutions having different polymer concentration. So here you can see that yes, like change the polymer concentration of this is ranging from 250 ppm to 2000 ppm. What it shows like at the low polymer concentration, the splashing effect, like in just water, these sort of small thin structures, they will readily fragment out. Here at 250 ppm, you can see the filaments eventually gets broken, the fragmentation is taking place. But as we increase the polymer concentration, these filaments are quite robust. They will always stay intact, and eventually, if we follow the whole experimental time frame, the filaments will eventually merge with the water. So basically, splashing is inhibited in these sort of scenarios. In the next slide, this is again magnet only. So the first case is water droplet on water film. The second droplet is viscoelastic droplet on water film. The third one is viscoelastic droplet on same viscoelastic film. Like the video is made in such a way that it will play at the same time. So before and I am telling. So this will, you can see here fragmentation will happen. Here, like there will be the rim instability and the crown formation will take place, but the secondary droplets which are formed at the tip of the filaments will stay. Here, the crown will not even form. It's like crown will form, but the secondary structures coming out from the rim, those will be not formed. Okay, so it is not playing. I guess. Let me just play the video. So let's just repeat one more time. So you can see in the first figure it will break. The second one there will be secondary structures. The third one there will be not even filaments coming out from the outside rim. So you can see right in the water case the secondary droplets are breaking out. This one viscoelastic droplet is water film. There is rim instability happening. But when it is viscoelastic droplet falling down on the viscoelastic film, there is no rim instability even. Okay. Now, water to air transfer and bubble. So we said that bubble bursting is also a prime mode of air transmission. What happens? Like let's say the bubble, the thin liquid film may contain pathogens. It can burst and release the virus or the pathogens in the air. So here, slided imaging is a form of technique. To the slided imaging, you can see a bubble and these small dots are the bacteria. So the slided imaging of bacteria, that is bubble. And these will stay as long as it is there. And it will not die out. So here the evaporation process is also an important thing to study. Now, many times it happens like let's say some bubble is resting on a solid surface. What happens? Because there is a spherical like this curved surface, due to the gravitation effect, there will be drainage of the film downward side, and eventually there is maybe some sort of hole formation is taking place, the bubble will burst. So these are the different stages of the bubble bursting that is captured here. So you can see eventually, like first initially there is some hole formation here, and as the hole like kind of spreading rapidly, there is emergence of the secondary droplets on the hemispherical cap, and ultimately it is bursting out.
The government of one quick second over here. So this is relevant for transmission, right? Now, can you guess, as if you think about someone who is infected, how is this phenomenon relevant for the pathogen from that person's body to go out into the air? Think about when someone is talking. We are closing our lips and opening it. It's like a bubble, it's like a film with cracks, bursts, and then it can create particles like this.
So bubbles, you know from the Young Laplace equation, there is the delta P equal to 2 sigma by r. This can be readily explained if you know the Young Laplace equation, which is delta P equal to sigma 1 by r1 plus 1 by r2. For hemispherical, the r1 and r2 will be same. So the pressure will be delta P equal to sigma by r. Then you can see, as I was saying, that once the hole is being formed, it is governed by the scalar quick relation, which is V equal to square root of 2 sigma. This rho W is the water density only, and H is the hemispherical cap height. So the refraction velocity of the hole, how fast the hole is being propagated through the bubble, that is given by this relation. So you can see that depending upon the surface tension, the Taylor quick relation is essentially saying that if you add surfactants, the whole propagation will be slow. Because surfactant, it reduces the like surface tension of the fluid. Now, H is the bubble thickness. So what happens here is the experimental observation. What it says that the bubbles, as it lasts longer and longer, due to this, like as I said, due to the gravity, the upper portion essentially kind of drains out the fluid towards the bottom side. The fluid, like the bubble, becomes thinner. So it is said that the older bubbles, which are more thinner, emit more smaller and faster droplets when it is bursting out compared to a younger bubble. Younger bubbles are more thicker. So these are all like experimental studies. On the other hand, there is another like competing phenomena, that is, like let's say, there is something called Marangoni flow. You know the Marangoni flow. So Marangoni flow happens due to the surface tension gradient. So like let's say there is a higher surface tension and lower surface tension. The lower surface tension fluid will be like here going over, or due to evaporation there is cooling happening. So at lower temperature we know that in case of water, surface tension increases with water. So if there is some sort of localized cooling here, then there will be increasing sigma compared to the ground one. So there is a surface tension gradient. So in the last slide, I said that gravity essentially tries to drain out the fluid from the top portion to the bottom portion. Here, due to the Marangoni flow, the reverse is happening. From the lower region, the fluid is trying to going towards the higher surface tension region. So that is basically like a reverse mechanism which will like what I can say, that will increase the duration of the bubble to stay. Essentially, like as the bubble becomes thinner, it has high tendency to burst out, right? So this Marangoni flow is like opposing that mechanism. So the Marangoni flow can happen due to temperature gradient, like bubbles emerging into cooler atmospheres. Like as I said, if like let's say some sort of localized cool air is blowing, then evaporative cooling, some sort of evaporation is taking place, then it is being like released, then there is cooling. Maybe there are chemical or biological compounds which is reducing the surface tension. That is also again leading to the like the variation in the surface tension. And sometimes it has been seen bacteria they can secrete some biopolymers which will lead to a change in the surface tension of the base fluid. That can also help in this sort of Marangoni flow. Next one are some general slides I just made long before. These are the like other motivations of studying evaporation. This can be like, let's say, from a healthy individual to a person who is sick. If we study the drying pattern of the evaporation, like the evaporating blood droplets, you can, I'm not going into the details, but the drying pattern of a healthy individual and a sick individual, depending upon, like, let's say someone is suffering from some blood related diseases, the drying pattern will be different in them. So Professor Saptosi Vasu is studying those sort of things. Many French PhDs are also studying. Then here the evaporation will also depend upon the what kind of surface, whether it is hydrophilic, whether it is superhydrophilic. The hydrophilic one will have more contact area, the superhydrophobic will have minimal contact area. So depending upon that also the evaporation rate is also dependent. Recently I saw in the, can you give me water in the water? So many of you have seen the David Wood's top paper. He came in to IIT Hyderabad. So he was studying the how to say, like the static splashing dynamics of blood. Like if someone hits you bullet from whichever directions, not you, it's like some poor victim. Blood, like the dying pattern of the blood splash, he have done, like they have collected from different directions. So basically what he did, he took many of his like lab students to collected the blood sample and he is like impacting that in different directions, studying the patterns. Then he has collected this database. This he has used as a like some sort of data model and he used AIML techniques to launch a app for the city where he stays. Take the photo of the splashing figure, the dried up splashing figure of that blood drop, and then he can help in the forensic analysis from which angle the bullet has been like hit, or like how the whether it is a blunt weapon or a sharp weapon, that sort of like some sort of insight into the criminal activities that he can, like at least he is claiming so. He has been working in that direction. So some like these are just this you can see like in a hydrophilic flow at the edges here will be the highest peak, like highest amount of evaporation rate. So what happens like this figure came in the context of copies can read many times, like there is this paper you can read later in a much more detail, like DEEGAN Nature I think 2000 paper. So this paper is just type coffee stain or coffee ring effect. What happens if we leave the coffee to dry? It forms a circular stain. So what happens essentially they are saying like at the edges the evaporation rate is highest. So fluids from these edges they are traveling to the outer periphery. So let's say a coffee drop, the whole fluid is essentially covered with coffee particles. Since at this surrounding the circle, the evaporation rate is highest, the coffee particles are essentially going rapidly outward and they accumulate in that this outer periphery and that leads to the drying up of the coffee particles leading like the ultimate coffee ring is formed. So there like subsequently there also have been studied how to suppress this coffee ring. Like what I would suggest at least first you can read the coffee ring effect. That is a very interesting 2-3 page paper only. So now just like briefly I am saying the modes of evaporation. One mode of evaporation is called the constant radius mode. Essentially you are seeing here that if we look, this is the initial droplet and the configuration. It gets pinned at one place and then it goes down. So you can see here from highest to lowest essentially means the volume is gradually reducing. However, since these points are fixed, you can see the radius is like constant. On the other hand, if we measure the contact angle is like the horizontal line and the periphery of these droplets, you can see the contact angle is decreasing. So this is called the constant radius mode. Likewise, the other mode is called constant angle mode. You can see here that it is actually gradually reducing gradually. So the radius is decreasing here, its radius is decreasing. but it is like a self-similar profile. The contact angles in most cases are constant. So you can see here the constant, like it is called the constant contact angle mode. Sorry, just this one, like the third one is called the hybrid, like it can also, like it can be a mixture of two cases, that is, it is called stick slide mode. There is like a constant radius mode you can see, and then the radius mode is falling. Correspondingly, this constant radius you can see the contact angle is decreasing, and the second part the contact angle is constant. So these are the typical modes which we normally encounter in evaporation. Then the last part contains the disease transmission in plants, where essentially you can see a drop falling on the horizontal surface creates some sort of crashing like this, whereas the leaves are generally hung like this, and leaves are also flexible surfaces. So when the droplet falls down like this, the leaf may also oscillate, and that may also lead to greater like transmission of the droplets when it breaks. So here you can see this is like, let's say, what if the leaf is just horizontal line, but what if the leaf is bent and it also simultaneously interact with the impacting droplet? Okay, so that is again some sort of fluid structure interaction problem. It can be like bungless, and some other BTech people, they started doing this experiment on a simple cantilever beam. Like obviously they are not as soft as the leaves, but nevertheless those beams are flexible. When it like, impacts a drop, it basically in some cases it fragments and spreads out, and in some cases it sticks to the surface. But that is again depending upon the droplet impact velocity. As well as like we are doing in polymers, the polymer concentration will also come into the picture. So here you can see that these are basically like after the fragmentation, what is the map of the pathogen footprint. So you can see here is a pathogen footprint when, like let's say there is a water film or a sessile drop. Just a simple water droplet is here. So water, how the fragmentation is creating the map of the dispersed droplets. So you can see here the different surfaces footprint of the dispersed droplets are different. Then these are the different sorts of, like this is called crescent moon fragmentation for a drop or drop impact. So instead of water film, if there is some sort of sessile droplet already reached, you can see it's like can be imagined as a half moon. That's why it's called crescent moon. So here also there is, like you can see that let's say this leaf is some sort of, as we like impact with the drop, the leaf is also interacting. So you can see this is due to this long filament, this is water here, the filament is breaking up. In our case, if we add like let's say 1500 or 2000 ppm, this filament will not break. It will stay with the leaf. Okay, so this is the final. When you are basically forming the governing equations, obviously the velocity you have to put, how the thickness profile, expected it is difficult, but it is not impossible to measure. People have sufficient, like some other advanced measurement techniques, or I don't know how they do more and more pathogen transmission. So I have discussed in brief about like several aspects, drop impact dynamics, splash dynamics, as well as like evaporation dynamics. And let's say in case of plant surfaces, drop impact on flexible surfaces. So I also have tried to connect with how our lab is trying to like explore this sort of dynamics, and we showed that like sometimes like the suppression of splashing, those things can be minimized by adding little bit of polymer in the fluid. So these are the summary, or like let's say these are the important hydrodynamic aspects which we try to cover briefly. That's all for this one. Then switch off. Maybe now maybe questions or maybe questions in the team. Done? Okay. So I realize that this sort of
the material that Dr. Shamanta does this on is an annual review paper by Lydia Gurika. She is very well known for the turbulent cloud dynamics and how things transmit in the air. So when he was talking about transmission, you probably did notice that it's mostly about what is going on once someone is expelling the electron. Right? Did you get that nuance while listening to the talk? It is all what is going on outside our body, not what we have been doing mostly in this class, which is inside our body. So as a result, one good thing about working in this field is most of the activity is, if you think about what is going on in terms of transmission mechanics, people have been looking at spatial transmission. And you can think about different categories of spatial transmission, starting from how these particles are formed, which is what he covered, and then how they are transmitting through the air, and then in different kinds of settings, classrooms, inside the car, in office buildings, etc. And there is a lot of activity in this field. So this is the busy field. What is the spatial dynamics, and thankfully many of the tools that people have been working on for how many years they could be applied here. And they don't have to worry about the anatomical complexity or the physiological complexity as one has said in this territory. Now what we did discuss is not this, right? We are talking about the transmission inside the system. So transmission of the infection onset mechanics. So therein lies the challenge of combining our fluid mechanisms for this with other things. Because the moment you enter the human body, you need to make sure that whatever flow regime you are at, it agrees with the realism of the system. Now, having done so, this particular session I want to keep it brief in the sense that let's just brainstorm. What possible future directions do you think people will need to work on based on what you learned for last 3 days? So, what do you think of the some areas where open questions could be raised? So, if you look at the lecture notes, I have to start this discussion. I have a page, the very last page. So, there I mentioned number 1 as the mucociliary transport. The reason being, while people have looked at ciliary hydrodynamics, people have looked at mucous rheology, but here you have to assemble that knowledge with the complex anatomical surface topology, as well as the fact that particulates with some nanoparticles are depositing on those droplets and moving with that. So, while the fluid mechanics knowledge is probably there in some areas, we need to merge that with the anatomical geometry that we have presented. And I have probably mentioned some points underneath there. Number 2, if I remember correctly, is the role of geometry. So, what is the flow geometry coupling? So, all our anatomical spaces have subtle differences. They're not alike. So, can we just look at the geometry, or can we just look at the medical scans and predict something about the transport patterns? And now again so the mucociliary transport is surface transport, right? Here we are talking about transport again through the cavity. So based on the geometry of the cavity enclosure, can we say something about the overall transport trends? So that area I think would need a lot of work, which would probably involve a lot of mathematical analysis as well. Because one side note from here would be, can we do some kind of shape analysis of the geometries. So this is a very mature field in mathematics. So we can, and this would be connected to the area called differential geometry, which could be used to track the nature of the surface changes, the nature in which the curvature of a surface will change around the globe. So this is a mature field. This is a very active field, and there are some open questions in that domain. The challenge is to connect them together. So I have recently written a proposal on this idea, but there are still many things that I myself don't understand in differential geometry. So that's what I was telling a student yesterday, that learning should never stop. So I started off from civil engineering, and this last Christmas when I had some alone time, I was basically studying differential geometry.
Instead of breaking up in concept.
Like many of you might know, this is like to give you some sense of what I'm talking about. If you think about coffee mug, okay? Think about pumping air. So there is a little hole, a little virtual hole. The hole is down there. Let's assume that you are injecting air into the mug, and injecting air as the mug deforms. What would be its eventual shape? Use your imagination. What would it look like once you think of a balloon which is initially in the shape of a coffee mug? You are injecting more air, pumping more air. Huh? It will burst. No, we are not going to get till the bursting stage. It's a mathematical problem. So, what shape eventually will it attain? Huh? Spherical? That's the wrong answer. Hyperbolic? That's the wrong answer either. That's the. Let me make the question simpler. If you have a rectangular block, now this is a block that is made of balloon. So a balloon which is somehow rectangular. You are pumping air. What will this become? Huh? A sphere, right? It will become a sphere eventually. Then what will the coffee mug become? It will become a torus. Right? Because of this
like something to do with the topological equivalent.
Yes. So because of this hole, that hole is going to be there no matter what. The rest of it would circle around that, overlap around that hole. So, and if you guys are interested in mathematics, so the 7 great problems of the Clay Mathematical Institute, which have the $1 million prize, only one of them was solved by Gregory Perelman. That was related to this kind of understanding. Anyway, so to go from here to here or here to here, you apply some kind of shape transformation to make the shape simpler, yet topologically equivalent. So that's what I'm thinking of. Can we make the shapes, the anatomical shapes, slightly simpler, not lose all the details, but make it simpler, keeping the topological equivalence true. And as a result, can we connect the signature of that topology with the flow transport patterns? It is going to be a challenging direction. Would need a lot of understanding of basic mathematics. But something to think of, because this by itself is a holy grail. Can we share something by just looking at the geometry and not run simulations every time or purposely? So number 3 that I have over there is, I think, role of evaporation and as a result, basically I'm talking about heat transfer. So as of now, when the particles are going into the airway, I do not consider any evaporation, right? So the simulations that we ran yesterday, they were not heat transfer simulations. But someone might argue that as the particles are going in, especially if you think about.
So actually, one line I read in that newspaper, like inside the system is like let's say 37 degrees Celsius, more or less. It may get released in a colder atmosphere or warmer atmosphere. So then that like the ambient mechanism that can change again the universal rate of those.
But that is Lydia's version. She is just thinking about the outside air.
Right.
Ejecting out. I'm talking about
What happens if you take this?
Yeah. Now, typically it's not an issue in the sense that if a particulate stays in there for less than a second, who cares what the evaporation is? But we also ran a MATLAB code that showed more than 2 minutes, right? More than 2 minutes, the particle going into the deeper channels of the map. We probably should include the heat transfer effect, but then everything becomes more complicated. So can we incorporate this in a simpler way or something that is still visible computationally? Can we identify the particulates which would stay within the air space long enough to be impacted by this heat transfer effect? Can we develop the science around it? That itself would be a 5-year gauge, basically. So number 4, which is basically something that a paper that I was writing then, probably is not that important, not as important as these first 3 topics, is on secondary infection. So since most of our simulations are geared towards finding the initial infection hotspot, what happens if particles from that region move further down or to other parts of the airway. And philosophically, this is similar to our subtopic in our other line of research, which I mentioned during my talk, is cancer flow physics. With cancer, I think all of us know here that we get cancer in a certain organ. Most of the times, we will die not from that cancer, but from metastasis. That cancer spreads to other organs. Philosophically, it's the same thing. So initially, the infection hotspot, you can treat that because it is sufficiently outlined with targeted drugs. But what if the infection goes to the lungs and it becomes very bad? Then it becomes weak. So similar to metastasis, right? You lose control of the infection. So the secondary infection dynamics, we have not seen much work in this territory yet. That's something that we need to think about as we move forward. So these are the 4 topics that I had figured out when I was writing the lecture notes. Each of them can easily stay one student active for the next 5 years. But beyond this, do you have any other topics that you can think of?
So, we have studied the particle motion by considering the full velocity as motion.
Yeah.
If both these are proper, then what will you do?
The linear flow is accelerating or having some kind of tumbling component. That we are already doing in the CFD. In the theoretical case, we did consider that to be an ambient steady flow, right? In the CFD, if you look at the visuals that I included, yes, the net flux is 30 liters per minute, but the time-dependent fluctuations are there. Numerically, we can still do that. So that is not the case. And if you are talking about someone breathing first at 50 liters per minute and that flux gradually increasing, that happens over a much longer time scale. If you are gradually increasing your breathing rate, that is the difference. And that does not have any particle transport relevance because the times per second are different. But theoretically, if you are trying to do that, yes, that would be something. Anything else? Okay, yeah, that's a valid point. So, deformable particles. And there is a lot of work in this area being done. Now, whether if you do consider deformability in the particulates, how does that eventually change the translational results? If they don't, then people are not going to take that kind of work because who cares? So this is how the science dynamics works, especially for interdisciplinary science. We mechanicians, we have a lot of details that we can
whether the details make any change in the eventual result, that's the key question. But of course, to know that you get the work done at least in a representative case. Anything else you can think of? Have they put some tea or snacks for us? Water is nice. You want take look? Yes. Okay, let's wrap up. I want to take a selfie with all of you, so can you move to this side?